Hi everyone, in this talk, I will present the paper DICE, Leveraging Sparsification for Out-of-Distribution Detection. This work is led by Eo and Sharon at the University of Wisconsin-Madison. This work studies the out-of-distribution detection problem. In a closed-world setting, it's often assumed that the training and testing distributions match each other. In the open world, a car may encounter objects such as a bicycle that is not in the training categories. Being able to identify OOD examples is important for deploying ML models in safety-critical domains. There has been many methods on post-hoc OOD detection, including maximum softmax probability, Odin score, energy score, and React in the feature space. However, previous methods primarily derive OOD scores using over-parameterized weights, while largely overlooking the role of sparsification. We provide a simple sparsification strategy termed DICE, which aims to bridge the gap. Now let me introduce how specifically DICE works. To begin with, we take a pre-trained network on Safari 10. During inference time, the input X will go through deep network and we get the feature embedding. The feature embedding will be forwarded through a dense layer and then we have the final output, which is the inner product between feature and weight. If we define the unit contribution to be the product of the unit activation and corresponding outgoing weight, the output for the class airplane will be the summation of the unit contribution. Now once we have the definition of the unit contribution, we can look at on average how each unit responds to the in-distribution data. So in the plot, the x-axis are the unit indices. On the y-axis, we show the average of the unit contribution, averaged across many in-distribution samples. The higher the y-axis is, the more relevant this unit is for this particular class. Actually, from the plot of unit contribution over all unit indices, we can clearly see that there are just a few units with substantial contributions to the prediction of the label airplane. To provide a direct evidence of this claim, we can actually sort the unit by its contribution. And on the right side, we have the most relevant unit with high contribution. And on the left side and the middle part, these are non-substantial units. From negative contribution to positive contribution, we note that there are a large portion of contribution with summation close to zero in both ID and OOD. These parts can be cancelled out for free. As a similar idea, we will plot the unit contribution when evaluated on some OOD like SVHN. The units are sorted in the same order as the in-distribution data. As we see, a large parts can also be cancelled out for OOD data. Based on this intuition, we propose our method as following. We firstly compute the unit contribution for each unit and weight pairs. Then we compute a binary mask by selecting top k largest unit contribution. Finally, we simply make a forward pass with the masked weight space. We then provide theoretical insight into why increasing sparsity level benefits OOD detection. Firstly, the distribution of output can be interpreted as a summation of m units contribution. It is clear from the figure that the summation from 0 to t has a zero expectation and non-zero variance. So by simply summing up from t to m we can get a distribution with the reduction of variance for free. Now we would like to show the empirical verification of our ideas. Initially, the output distribution without any sparsity appears to have a larger variance. Increasing sparsity levels results in a sharper distribution, which benefits OOD detection. We also compare DICE with competitive methods in the literature. Our results suggest that DICE is overall the most competitive methods on both common benchmarks and large-scale evaluations. We provide other important experiments and discussions. Check our paper for more details. Thank you for listening. Our code link is available if you are interested.